So in a late change to the lineup, but the same presentation, just a different presenter, Matthias Galitz from Dekema Research Institute is going to be talking about coating, surface treatments, alloying strategies to enhance material resistance in these extreme material environments, including combating metal dusting and oxidation. So Matthias, over to you. Thank you.
Thank you for the introduction. Is that on? Yeah? Okay. Yeah, good morning, everybody. We have a last-minute speaker change. So my name is Matthias Galitz. I come from the Dekema Research Institute. Emma, unfortunately, who was supposed to give this presentation, is out of the cold at the moment. I'm probably the closest of you all. I had to travel like 5 minutes from our institute. We are located here in Frankfurt, really 5 minutes from the fairground. And we do a lot of high temperature exposures. And in this turn, we were looking at new high temperature materials or newly printed high temperature materials. So here are some examples. Is this? No. Do I have a pointer here? No? Okay, no pointer. Okay. So what you can see here on these slides are all components that are very interesting for the chemical industry. That might not be the first thing that comes to mind, but they are, when you have critical, harsh conditions in some chemical plants, you corrode those parts quite a lot, and it would be very interesting to replace them on site, because the real problem with those plants are the downtimes, basically. So when you imagine you have somewhere around the world, you have such a chemical plant, for example in the Middle East, that was built by a European or American company, and then you have a severe corrosion mechanism in place, and one of those parts is failing. You have to find the manufacturer. It takes a long time. So here additive is really interesting. And on top of that, of course, you can realize parts, and you all know that you're the experts in this field, with cooling channels, for example, that you could never do with a classical manufacturing method. So these are the two main drivers for AM in this field. So here's an example. In many industrial plants, for example, we have syngas, which is a mixture of CO and H2. H2 is becoming more and more, aware even to the public that this is important, but also CO. It's called synthesis gas for a reason, because you can make basically all the chemicals, syn fuels, you can make almost everything, the whole carbon world, from this gas. At the moment, we get this from steam reforming, basically, of natural gas. In the future, we can do this via co-electrolysis from CO2 and H2O. And dry reforming is another method that goes way into details now. But the main two are these. Now, the problem with this gas is it causes a severe kind of corrosion at around 600, 650 C that is eating up the plants pretty fast. Interestingly, above that temperature, the scales, for example, alumina or chromia, that form protective scales on the metals, grow faster. Also, the mechanism goes down from the carbon activity. And below that, for example, the kinetics are too slow, under 400. So it's really this medium temperatures that are the most severe. What happens here, and I know that you are all AM experts, I just would quickly summarize this corrosion mechanism. You have this high carbon activity, and it wants to form coke. So maybe you have heard of carbon nanotube formation. That is also made out of this gas or different gases. And this is basically the same mechanism. We form graphite in the material, and this is eating up the material and turning it into metal dusting. So this is why this mechanism is also called metal dusting. When this occurs, it's usually too late, so we need a long incubation time, what this is called, until this mechanism comes into place. Then in a few hours it can go millimeters deep, basically, in your material. It also has a high risk. What you form are those pits, and this is a picture from our lab on the right, where the alumina crucible that you can see in the back could not hold the sample anymore because of all the graphite that is produced there. It's completely crushed, and the sample is in the middle of this, what looks like the center of those graphite strings. So the two approaches that are usually done is to form a barrier on your surface to protect the material from these gases, or to have a catalytic inhibition of the carbon uptake. And there, this alloy was developed, which has extremely high chromium content, as you can see, with 29.5%, some aluminum and some other additionals for these particular environments. So today, it's not only about this particular alloy, but the takeaways are basically applicable to all nickel-based alloys that are printed and meant for high temperatures. So this is the scope and what I would like to show you today. Metal dusting is kind of the example for that here. So as you can see here, these were laser powder bed fusioned pieces with our collaboration, VDM Metals. So they build it. Here you can see that the surface on the bottom is the as-built surface, of course rough. After exposure, still we don't see much attack. Above that, the same when we have them just ground to 1200 grit. And on the top is the conventional hot rolled mill ground material. So generally, the AM is good, obviously, for metal dusting resistance. And from the alloy point of view, it's similar to the base material, to the conventional. The problem is a little bit that we have those rough surfaces. And when you look in closer via the SEM, what you can see here is that you have some carbon deposition. It's without the pointer. It's a little bit hard to see. Maybe when you have a ground surface or a flat surface, we don't have those kind of weak spots. And when you look at those, and the top is the as-built, on the bottom, solution annealed after the different temperatures. You can see it here on the surface already. And on the as-built ones, we start to find some small graphite. Also, it's not severe. The alloy itself is quite resistant, as I said, but we start to find the evidence of attack, while for the ground material, this is not the case. So obviously what we need for this type of corrosion is a surface treatment, and also the alloys themselves, they need a heat treatment usually after the building process when you want to use them for high temperatures. So they need to be solution annealed, because you have a lot of aluminum in there. You have other elements that during the AM process basically form precipitates that are unwanted. So we need to solution those and then reprecipitate them for the highest strengths. Now the problem is here with the solution annealing, there's some aluminum in those alloys, and especially aluminum oxidizes at very, very low oxygen partial pressures. So during the solution annealing, you can see here that some aluminum close to the surface was internally oxidized already. And of course, this is a weakening the later corrosion behavior. So this is something that you should keep in mind, and this is another reason why a final surface treatment is necessary. Now, the interesting part is, what do you pick as a surface treatment? I mean, in the lab, we make it easy. We just grind everything. On an industrial scale, that's quite tough to do. And so, on the left side, you can see different samples where one side was on the top mill ground. So this is something that you can actually do. Then in the middle, you can see a shot peen sample, obviously not performing great. Now you can already see those pits that show clearly the metal dusting, and the same is true with shot peening and mild pickling. So when we look below the surface on the right, in the cross sections, you can see the mill ground, the shot peen and the shot peened and pickled. And here you can already see, like, this is now the cross section of this pit where the attack was. You can see some deformation below the surface, but that should usually not be such a big problem for the corrosion and metal dusting behavior. What we found, on the other hand, is significant amounts of iron. And iron on the surface from the shot peening process, basically, this was an industrial shot peening process where lots of materials go through. So of course you also have, even in the peening process, this was a nickel-based alloy that is basically iron-free. But obviously in the shot peening, before that there were some austenitic steels, for example, some other steels. And the residues of those can be found on the surface. And iron is very active and very catalytically active with this carbon deposition. So the post-processing basically distinguished or decided if this material is resistant in the application or not. So I would like just to raise the awareness that the AM is great, but be kind of a little bit careful in the end when you pick your final treatment, especially when you go to corrosive environments. When it comes to solution annealing as well as the surface treatment. Another approach is, and I showed you this initially, to use a catalytic inhibition. And there, copper is known very well to prevent this attack. The carbon cannot, easily spoken, it cannot really connect to the material once you have copper in there. So that suppresses it. This is a literature study. This was the first one from Nishiyama in 2005 that was proposed and found in Japan that when you have 20% of more copper, then basically metal dusting cannot occur anymore. So from an industrial point of view, the closest to that is basically an alloy 400. The composition is shown up here. The balance is again nickel. It has it fulfills the requirement of more than 20% copper. So we have about 30. We have a little bit of manganese and a little bit of iron in it. Again, we exposed it in our labs. And what you can see here on the bottom is the conventional ground material, and it's all black. After 960 hours, so almost 1,000 hours, then the AM400 printed in this case, even the as printed, is obviously better. It lasts longer. Also, finally, it turns black too, as does the ground material. So it seems that the AM has a better protective behavior, but obviously this alloy itself doesn't show what the lab alloys show when you just have nickel and copper. And the reason for that is that there's a little bit of iron and manganese in it. And we have seen before that iron can be quite detrimental. So we tried, and here after 1,440 hours, same exposure basically, when you leave out the iron and the manganese, we don't have this type of attack. So a slight change, and this is something that we can also do way more easily with AM methods in the powder composition, can determine if we have the corrosive attack or not. So this gives us a nice way to really design the materials, and in this case it's even more funny, because when we have iron and manganese in it, the corrosion is pretty strong. As soon as we leave out one of the two components, the corrosion decreases immediately. So this is a good opportunity to design the powders and remove the manganese and the iron. So here, this is then again same shown just as weight gain data. Here you can see the 0 manganese, 1%, 2%. So it really scales directly. Same is true here with iron, and then the manganese alloy in comparison. Once you take out those impurities, the corrosion resistance really goes up. So here you can see again the attack on the left with 1% manganese. We find slight pits still. This is 100 microns. This is the top view, and then on the right with 2%, much bigger pits already in the cross section. So what can you do? You could also try to combine this heat treatment that you have to do anyway for those nickel-based alloys with a coating process. And one coating process is the pack cementation that has been around for more than 100 years. It was patented in 1906 for aluminum. Basically what you do, you mix a powder of the coating element and you put your part into it. You need a little bit of extra activators, and then during a heat treatment you basically apply the coating. And here this works perfectly. We get a thin chromium diffusion layer on top, so we have a double protection from the barrier along with a catalytic inhibition of the copper. And then basically so far, this is the bottom. This is currently continuing this exposure, but we are very hopeful that basically by this combination we can completely prevent the metal dusting. And now the idea is basically, since we need a post-processing anyway, to combine this with the coating technique, to first pick also the right post-processing, and especially in harsh environments that might be key if your part fails or can last much, much longer. So probably this was the first time you have heard of metal dusting. Sorry for that. I know this is not the main focus, but I think the post-processing of AM and this awareness for high temperatures, when you print parts, you have oxidation, you have corrosion. I hope that I could raise that a little bit. And yeah, if you have further questions later, as I said, we are close by here. It's in Frankfurt, 10 minutes walk. We have the huge research labs. It's not what you expect in this bank district, but that's what it is. As I said, surface treatment is key. The heat treatment as well, because you might form internal oxides. You can change your alloys not only in the way that you want to. We need to basically work on this roughness and porosity when it comes to an oxidation point of view, because just the large surface is basically prone for corrosion and attack. And this combination of a post-heat treatment, for example, with a coating process, might be a very good way and path forward. I would like to thank the partners and mention the EU for funding. This has been all part of the Top AM EU-funded project. Okay, it's getting harder and harder to hear, probably. Sorry. But yeah, our partners, it was a large consortium, as you can see, within Europe. It was a really nice collaboration. It's coming to an end actually this month. But yeah, so I'm glad that I could share some of the results with you. And the last thing is to thank my co-workers, the high temperature corrosion team, and especially Emma up here, who couldn't make it, and you got me instead. So thank you for the attention. And yeah, if there are one or two questions, maybe one question, time-wise, I'm happy.
If you have a question, I can bring you the microphone. If not, where can they find out more? They can go to the website, the Spire 2050, or take a walk.
Or just shoot us an email. Yeah.
Okay.
Thank you very much.
Matthias, thank you very much for stepping in at the last minute.